welcome to the House of ZK Radio, which is a focused podcast and media channel exploring everything ZK, zero knowledge. Hi everyone, welcome to the House of ZK Radio podcast. My name is Alice. I am the primary host of House of ZK, and I'm joined here today with Ismael, who is the CEO of Lagrange Labs. Really excited to have you here today, Ismael.
Thank you so much for having us, Alice.
Yeah, thank you.
We've seen a lot on Twitter of House of ZK over the last several months, and we're very excited to finally be on.
Yeah, I appreciate it, and really excited that you're also here in DEF CON today so we can do the in-person recording.
I know. I always feel like in-person podcasts have just a much better vibe to them.
Oh, I agree, definitely.
Luckily, the timing worked out.
Yes, definitely. I'm wondering, Ismael, if we can first start off with an introduction of yourself, so maybe how you got into the Web3 and specifically the ZK spaces.
Yeah, so my name's Ismael. I'm the co-founder of Lagrange. I got into the ZK space originally when I was working at a large insurance company in Web2, or TradFi, in fact, Manulife John Hancock. And we were working on building early embodiments of decentralized insurance products during the first DeFi summer. You know, markets get hot, and then a bunch of late entrants like TradFi providers are interested in, figuring out whether or not they can get a piece of it. And so they hired a team, and I was leading an engineering team there that was working on early decentralized insurance products. And one of the main issues that we faced was over keeping client information private if we were going to use on-chain insurance or reinsurance platforms. And so that was the first time we kind of touched ZK, or it's the first time I kind of touched ZK. And it was really kind of brought about by a practical necessity of using zero knowledge. And, years later, I was a venture investor for a while. And when I founded Lagrange, I felt that there was a substantial amount of opportunity for using a fundamentally novel technology to really deliver significant value to end user applications. And so one of the first hires we had at the company, Babis Papamonthu, he's the chair of the cryptography department at Yale. Obviously, his background in ZK is of a purely academic nature. He's been obviously a professor, and he did his PhD focusing on zero knowledge cryptography. But for me, I really kind of found it always incredibly impactful as a business-facing enabler.
Yeah, definitely. And you had quite an interesting background as well because you came from the investing side and then you're also a co-founder. So I'm wondering if there were any sort of new perspectives you developed from being an investor that you applied to being a startup founder.
Yeah.
Just wondering about that.
That's a fantastic question. So I think the framing with which you look at a problem is something that you're trained to do as a venture investor, particularly in Web 2. Where you think about the value chain of an industry and you think about wherein you want to place a bet in that value chain. And I think as an operator, you make that same decision, but you just have to have a much higher level of specificity because you only have one bet to make. And when we looked at crypto, what I really felt was that verifiable computation was the only way to meaningfully scale the execution that is possible on-chain and to enable applications that exist on-chain to do things that they otherwise couldn't. It was really this 0 to 1 moment for the space, and it will be this kind of transformational piece of technology when we see it used by every application. And there's a story I like to tell that several years ago I was in the Bay, and someone said to me that every application is going to be a cross-chain application. Every DEX, every lending app, every NFT protocol, really any consumer app will be cross-chain at some point. And at the time, it was a very bold prediction because cross-chain was very new, and we still hadn't seen Ethereum achieve the roll-up vision, and really people were just building in isolated ecosystems. And now, if we look at it, almost every DeFi app has either a wrapped asset it supports or has a cross-chain deployment. And so the prediction I've been making is that we're invariably going to see every app be a ZK app, whether it uses exogenous data brought on chain through ZK TLS, whether it uses execution that's extended with a coprocessor, or whether it uses a verifiable execution space like a ZK rollup.
Oh, nice. And just wondering, like you mentioned that eventually all apps will become ZK apps, but wondering if we can touch a bit about the challenges that come, like for developers on building these ZK apps. Why haven't we seen mainstream adoption as of now?
Yeah. So I would say that we are beginning to see mainstream adoption. So we're working, or Lagrange is working with a lot of the top on-chain application builders. So we work with folks like Azuki, we work with folks like Gearbox, EtherFi, Renzo, like serious DeFi protocols and consumer protocols are actually taking first steps. And there's a number of other ones that I can't list here, but they're tier one dApps. And I think what we've seen with ZK that's been an issue has been the developer ergonomics of using it, the cost of using it, and the latency to use it. And frankly, the cost and latency are often just a trade-off in systems. But the price constraints and then the ergonomics of using it have been, to date, very difficult for most developers.
So cost, latency, and then also just the developer experience as
exactly.
well. Yeah, I see. And just also wondering about the application side. So you talked a bit about ZK-TLS. I'm wondering if there's any other sorts of use cases that you're personally very excited to be built with ZK or on Lagrange as well. Yeah,
so I should take a step back. Lagrange isn't building a ZK-TLS app, so I want to make sure I do caveat that. So what Lagrange focuses on is two core things. The first one is our ZK coprocessor, which is, put simply, a way to extend computation for a smart contract, to make an asynchronous call to request a computation that would be too intensive to run in the contract as is, and to receive an asynchronous result back that you can verify. That's what we work on with most of our dApp partners. The second thing we focus on is decentralized proving. So we have a production network that's been in production for about 4 months at this point. We have about 85 institutional operators participating who are generating proofs for us. And it is able to very efficiently serve a very complex set of heterogeneous proof requests and proof demands. And so that at its core is what we kind of think of the future and the core of Lagrange. So the direct application that we sell to dApps, the coprocessor, and then obviously the broader network that delivers that computation.
Got it. And then you mentioned Lagrange's network is also decentralized. I'm wondering if you can speak about the implications of decentralizing a proving network and kind of what benefits that brings.
Yeah. So one of the things I loved about crypto originally was this idea of this unstoppable programs or unstoppable code. You could deploy a dApp on a public blockchain, and that dApp could execute its computation in perpetuity. No government could stop it. No individual could stop it. The team couldn't shut it off. If the contract isn't upgradable, then it would exist in permanence. And that's something you don't see anywhere else. But that inherently includes this concept of liveness. And now we're talking about the use of verifiable computation to extend what a smart contract can do, to create verifiable execution spaces or bring in exogenous data. If these primitives that use ZK don't have liveness, then we haven't done anything that couldn't be done with a database, right? We have safety guaranteed, but we don't have the ability of that code to operate independent of a third-party actor. And so that's where liveness matters for proving. If we want to build this egalitarian, open, decentralized, equitable financial rail, and we predicate the entire thing on a centralized prover that's running in AWS, we haven't meaningfully adjusted, or we haven't meaningfully taken a step as a space. And so I think of decentralized proving as the logical evolution of proving. It's the one that aligns it with the ethos of crypto.
Yeah, so those kinds of liveness guarantees are really the main value proposition behind decentralizing proving network. Got it. And also wondering just about you guys. I know that you guys, for your proving network, it's being built on EigenLayer. So I'm wondering if you can speak about like some of the thinking that went about with that decision, or some of the advantages that you saw being provided by building on EigenLayer. Yeah.
So at its core, when you evaluate the cost of a network, you have to think of the operating cost of running a node and then the capital costs associated with the stake that goes into those nodes. And so that typically, in blockchains, typically capital cost is the highest proportionate cost. So if you build a Tendermint chain today and it stakes Ismael token, the amount I'd have to pay to incentivize people to purchase Ismael token and then delegate it into validators is going to be a lot higher than what the validators actually have to pay to exist. And so when you think of ZK, though, you kind of flip that dynamic, wherein you only have to guarantee liveness with the decentralized proving, but you have a much higher operating cost. The cost of generating a proof, in most cases, is the bulk of what a user is paying for. And so if you pair a high capital cost with a high operating cost, you have networks that are infeasible to build at scale. This is why if we see a lot of the DeepIn networks that people built in the last cycle on the Cosmos, very few were durable, because you would need 30, 40, 50% annual inflation rates, which just destroyed the value of the asset. And so this is why we needed to find an area where we could use low capital cost. And what Eigenlayer offers fundamentally is the lowest capital cost in crypto, from 5 bips, 10 bips on restaked ETH, compared to 30%, 20%, 15% that Cosmos chains are paying for native token staking.
Got it. So really trying to optimize for those costs to be as low as possible. Yeah, that's definitely, even for like proof generation costs, that's one of the biggest barriers that come with generating these ZK proofs. But as time goes on, hopefully we see those kind of costs lowering and making it more accessible to more developers.
Exactly.
Yeah. So I'm wondering also about if you could speak about like the current problems that we see with our prover marketplaces. So maybe some things like relating to incentive misalignment or collusion risks, perhaps general efficiency. Just wondering about your perspectives on our challenges within our prover marketplaces.
I'll take a step back and I'll make a contentious point that hopefully gets clipped maybe. But what I'll say is nobody uses prover networks and prover markets right now. Like none of the commercially available prover networks and prover markets have any users besides those that are built by companies that actually build an underlying proving system alongside it. Like the general purpose prover networks and prover markets, the ones that are live, have very little organic demand. It's mostly just farmers and them trying to pump numbers for a fundraise. The reality is the incentives on those networks aren't great. There's really no compelling reason to use those networks instead of just deploying your own compute environment. And they all have technical limitations. And so I can start by enumerating some of the issues that we saw on this. So firstly, none of them really have very efficient auction design implemented within them. And none of them are incentive compatible. Secondly, a lot of them are using POS chains, which causes issues with capital costs for the overall network, which means that users aren't just paying for proving costs, they're paying for the underlying cost of the stake that's used to handle the orchestration of proofs. So they're very expensive to use. They also have horrible latency because you have to generally do global ordering on their POS design, and then they do like a round-robin stake-based assignment. Like I'm not going to name any, but a lot are doing that, which isn't incentive compatible. And so overall, there's not really a great reason to use those. Like moving from centralized to decentralized proving to guarantee liveness is fantastic ideologically, but it has to be practical from a technology standpoint for anyone to choose to do it. And so we saw these problems, and as a team that focused on building a fundamental proving system, we realized we had to build a network ourselves, because otherwise we had no options of how to do our proving in a decentralized fashion. So we initially built our proving infrastructure just for us. And then over time, we realized that a lot of our partner teams wanted something that worked for them. And so we have a bunch of functionality in there that's actually designed by people who needed to do decentralized proving for their own applications. We have an incentive-compatible auction design, DARA, that was developed by a research team. It's a paper, it's out now. We submitted to Financial Cryptography this year. We have this concept of sub-networks within the network that have the ability to specialize in different proof types based on hardware requirements as well as different economic considerations. And what this really functionally enables is a network that is both universal and customizable and specific. So you don't really trade off performance for specialization. We also have like very strong institutional provers who are already on the network and already running provers for us. So we have like very good SLAs overall, and then it's also incredibly fast. because this is not trying to fit every single proving system into a giant funnel, which has a bunch of a bunch of the aforementioned bandwidth constraints will result from. But it allows the network to really kind of isolate how it's doing different types of proving dynamically and composably.
Got it. And I really like that idea with provers being able to specialize within different proofs depending on kind of their hardware requirements, depending on what they're going for. So I feel like that specialization aspect really kind of helps with this. So really great to hear that. Also, just wondering about just on the topic of incentive misalignment, what do you believe are the root causes for it? Why is it that we end up with scenarios where users are paying more than what they expected and provers are not like earning as much as they should? Why is it that we have that kind of like dichotomy there?
There's a lot of problems that kind of conflate into this. Firstly, like broader network efficiency is incredibly important. And the example I give, assume you have a roll-up that's using a prover market, and that prover market has 2 provers, and each of them bid to generate a proof. And a batch comes in and they bid. They each have a utilization rate of, let's say, 50%. They bid, one wins, the other one wins, one wins, the other one wins. They continually bid competitively. And so that means that the cost they have to charge to generate that batch proof, that proof for a given batch of transactions, has to be 2x what a centralized prover would do, because their utilization rate on their machines is 50%. And they have to at least cover the cost of the machines, and it's not going to be utilized fully. And so this is some of the dynamics that these prover markets face. And people don't often talk about this because the architectures are very nascent. But now you consider it a giant network of a bunch of people bidding. And sure, you'll see decaying price over time naturally, as markets do. But you'll also see like huge increases in cost because the network is not efficiently maximizing for utilization. And then you look at the other way and you say, okay, well, what if we just do we do a round robin assignment, everybody gets something all the time, so that nobody has this issue with not being utilized. Well, in that case, you're not actually creating any pressure on price because you have no incentive as an operator or a prover to actually optimize your setup. And so these are the types of issues people hit in these markets, and this is why they're expensive and they're right now kind of toys. What we needed to build, and what our team has built, was an auction mechanism, DARA, that is specifically designed for resource allocation within resource markets, or work allocation within resource markets, right? We took a step back. We looked at the EIP 1559 work from related to Ethereum. We looked at the set of properties that were defined for a network to be incentive compatible. We looked at how the TFM worked, and our research team wrote a work that tried to optimize for those same properties through the mechanism design within each of the subnetworks. And so we gained properties like fair pricing, collusion resistance, computational efficiency, budget balancing, welfare maximizing, and we were able to kind of reach this final state that's a lot more performant. And then beyond that, there's some stuff that aren't research. It's just plain old engineering. And that is, how do you build things that are able to take the request to generate a proof and build a query plan or a computational plan across the network that maximizes machine utilization? And how do you allow teams that want to build on top of you to have building blocks to try to leverage those in the subnetworks that they create?
I see, yeah. And just wondering about DARS specifically, how do you guys deal with the collusion risks?
Yeah, so it's the way the auction works, the way the double auction works, and the way the pricing works in the auction. We have a mechanism that is used to match the bidders and sellers within the auction, and the way it does that matching stops against collusion.
I see. Okay. And also wondering a bit about the roles as well. So like say with between the provers, the proof requesters, the actual protocol itself, how does DARA really shape the roles within that proof generation system? So it's actually, the paper is actually fantastic for anyone who's watching and really wants to dig in. It's out right now. We have formal proofs of all the properties that I'm talking about. But broadly within each subnetwork that we talk about, we have a gateway that's responsible for conducting the auction. We have what we call a scheduler, which is responsible for kind of taking incoming requests and parsing those requests into a computational graph that can be distributed out the network, and then a bunch of provers who've subscribed to generate proofs for that given gateway.
And Dara kind of sits in the middle of the provers and the gateway. It's kind of the substrate with which the network is able to kind of delegate work, and provers are able to specify kind of cost preferences and obviously size preferences for the types of work that they want to do.
Got it. And I really like how provers are able to specify kind of those parameters that they're going for. And we talked a lot about the prover network side within Lagrange. I'm wondering if we can also talk a bit about the coprocessor side that you guys offer as well. But just wondering if you could touch on the value proposition that like ZK coprocessors bring to the space.
Yeah. So what I think the roll-up vision of Ethereum got right was using verifiable off-chain computation to scale execution. What the roll-up vision struggles with is that it separates both state and execution from the layer that the rollup settles on. So an L2 separates state and execution from Ethereum. It has its own state root, it has its own blocks, it has its own state transition function. And an L3 separates that from the L2. The problem with that is you face asynchronous issues over how applications that sit on multiple chains can communicate. And it's a very different engineering paradigm. That's why most applications that we see that are cross-chain native just have two separate deployments that can send assets. They don't really span multiple chains. What a coprocessor does is it lets you separate execution without separating state. So you can take things within your smart contract that are expensive, that are computationally heavy, and you can do them off-chain and prove them back on-chain. But what you're proving is a computation of the data of the chain that the proof is verified on, not a computation over a separate state like a rollup does. And so by separating execution without separating state, you can take blockchains and you can take applications from exactly where they are, and you can keep them where they are and just let them do a little bit more.
Got it. And so I'm wondering just about the design considerations behind the coprocessor that Lagrange is building. And then I know that you guys have also, I saw in your documentation, you're using the ZK MapReduce for recursive proving as well. So just wanted to discuss about some of the motivations behind these design considerations. Yeah.
So the ZK coprocessor is something that is very dear to my heart, as it's one of the core research areas that Lagrange has pursued for the better part of 2 years. And so what I love about the ZK coprocessor is it takes the question of scaling computation and it applies that into a front-end language that a lot of users are familiar with computing over data, SQL. And so a user can specify a query in SQL that would run over blockchain data, the same way they'd write it in Dune, and we're able to parse that SQL statement into what is called an abstract syntax tree of how the data is manipulated, and then prove each operation in the abstract syntax tree in parallel. And what that lets us do is to let developers kind of write very data-intensive computations over blockchain data in the same way they would in Dune, and then verify that back in their contract. And so as opposed to like a ZK VM with like a RISC-V or a WASM backend where you're writing Rust or you're writing JavaScript or Solidity that you're gonna compile down, or C that you're gonna compile down to RISC-V, you write that in SQL, which we think is a very natural language for expressing computation over data. And so this sits on top of a paper we had previously called RECL trees. And RECL trees are a vector commitment that is updatable in logarithmic time. And this is kind of the basic idea of this ZK MapReduce. We have a data structure, and you want to structure a computation over some subset of leaves in that data structure, in the same way you would over storage or transactions or receipts in a blockchain. And then you want to be able to update that computation dynamically. There's an extension of RECL trees called RECL plus trees that we also cover in the paper that takes this abstraction of this kind of PCD-based batch proof and enables you to put flexible computation over all the branch nodes and all the leaf nodes. And that's where we get to MapReduce, where every leaf element is computing something over it's computing a map step over some data element, and then every branch is computing a composition of two of the dependent branches or leaves. And then we're able to kind of map SQL in this new paper we have coming out called Perseus, a lot of papers, but we're able to map the new paper, the SQL to MapReduce, and that gives us this kind of ability within the coprocessor to structure computation over blockchain data in a way that really scales.
I see. And I really like how you guys are really optimizing for that developer experience, especially since a lot of devs, they already are familiar with SQL and they're able to just write queries. And I do see a trend nowadays where devs don't have to write the ZK circuits directly, but instead there's more abstraction layers like what you mentioned with ZK VMs. Devs can write Rust, C languages they're already familiar with, and then for Lagrange's case, just SQL queries, which I think is pretty powerful. So that's really great to hear. Also wondering about some of the use cases that you're personally excited about for ZK coprocessors or ones that Lagrange is are planning to adopt in the near future.
Yeah. So I think we naturally see this thing in crypto where developers tend to build to the technology that's available when they identify a problem space. So they said, okay, I'm going to build a DeFi app. And they say, what's the technology that's available? How do I write a DeFi app in Solidity? And then they build the app to the tools that was available day one. And it takes time for them to adopt a new set of tools once the thing they build is already in production. And it takes time from a developer who came up on a certain set of tools to begin working on a new set. And so, I think early versions of ZK coprocessors or ZK VMs really struggled to find PMF on chain because dApps just don't want to use it. They don't want to use it. And so we really went out and talked to developers. We talked to NFT developers, we talked to DeFi developers, and we just figured out what they were doing. And all of these apps, specifically DeFi, there's like something hidden in all of them, kind of in the back room, like a Python script somewhere that they use to update some parameter that they would rather put on chain and they'd rather put in ZK. You just have to find that thing. And so, Mike from EtherFi, one of our partners, he talks about rebasing and LRTs as an example of that. And that's a use case I'm very excited about. And another thing that we've been working on with that team is actually a cashback program for their credit card. They have an on-chain credit card that is able to enable you to transact on top of your balance within their EtherFi app. They have about 5 billion TVL right now. That's rather substantive in terms of what their customer base has put in there. But in order to enable you to do that and to transact and then get cash back on your transaction, they need to be able to do types of computation that Solidity just doesn't support. And the only way to do that is with a coprocessor. And so we've been working with them on that for a while. And on the other side of the coin, another team, Azuki's, they're one of the top kind of creative NFT IPs in the space right now. They focus really on kind of this anime style, this intersection of like anime and art and creative. And so they are working on a bunch of collectors programs as well as kind of immersive digital experiences that are based on top of ZK.
Nice. And just relating to also the use cases, I wanted to tie that to just your overall vision for the space. So how do you see the space evolving in the next few years, and what does the kind of the end game look like for you in terms of ZK?
Yeah. So I see the space moving to where every application will use ZK. Every application will use zero knowledge for its data, for its bridging, for its co-processing, for the execution spaces it sits on. It will be as intertwined into the fabric of crypto as consensus is. And to get to that point, we need highly efficient proving. We need, frankly, liveness guarantees on that proving. And we need crypto infrastructure that can support a heterogeneity of innovation on proving systems. And that is really where Lagrange sits. We are a ZK team that builds coprocessors, and we build a network that is able to deliver value to both our coprocessor and then a bunch of our friends as well, who also want to be part of this future vision.
Nice. Really loved how kind of all of it you guys do really tie back to the vision that you're supporting. So really good to see that.
Appreciate that.
And yeah, of course. And just as a last question before we close up, I'm wondering if you want to give any announcements on behalf of Lagrange, or if you have any sorts of advice for our audience.
Yeah. My advice would be ask yourself that if the computation that you could do on chain had no limits, what would you build? If you could access any exogenous off-chain data, if you had trustless cross-chain interop, if you had unlimited computation on your execution space, and if you had shared liquidity across all the execution spaces you could deploy on, what would you build? And by asking that question, I think you can get to architectures that are in order of magnitude better than what can be built on, OPL2 or on Ethereum mainnet, and they're all foundationally powered by ZK. And I would also say you should follow Lagrange on Twitter, because we have some big announcements coming out in the next few months related to our prover network and our coprocessor.
Nice, nice. Yeah, that's a really big question that we should ask ourselves even as well. So thank you for bringing that up. And also thank you so much for all your insights today. Really enjoyed hearing what you guys are building on both the coprocessor and the prover network side.
Thank you so
much for being here. Thank you.
Thank you.
All right.